So we know that the Taylor series, it states that any functions can be represented as the sum of infinite terms. So as per the Taylor's equations, the cos x can be represented as sigma n equal to 0 to infinity minus 1 power n x power 2n all divided by 2n factorial. Similarly, the sin x, the sine function, can be represented in infinity term as n equal to 0 to infinity minus 1 power n x power 2n plus 1 all divided by 2n plus 1 factorial. Now I am going to expand this term, the cos x term and sin x terms, by increasing the value of n from 0 to 4. Now let's see that what is cos x. Cos x will be like 1 minus x squared by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial, and it goes on. So n will change from 0 to infinity. So if I put n equal to 0 here, minus 1 all power 0 is 1, and x power 0 is 1, and 0 factorial is 1. So it is 1. So when n equal to 1, so minus 1 power 1 is minus 1, and x power 2 into 1 is x square by 2 into 1 all factorial is 2 factorial. So when n equal to 3, minus 1 all power so when equal to 2, minus 1 all power 2 is plus, and x power 2 into 2 is x power 4 divided by 2 into 2 all factorial x power 4. And similarly, we can represent x sin x in terms of infinity series. So sin x, similarly, we can expand as x minus x cubed by 3 factorial plus x power 5 divided by 5 factorial minus x power 7 divided by 7 factorial. So it goes on. So we obviously feel that so when I add all these infinite series terms, does it produce a cos wave? And does this one produce a sine wave? Oh, it's different. And now I'm going to check whether this the sum of infinitive terms produce a sine function and cos function. I'm now taking to plotting this function using a graph. Okay, now I'm going to plot the cos x function by combining all these infinitive terms, and let's start. So cos x term is 1 minus, so x power 2 all divided by, that is 2 factorial, that is 2 factorial, the plus x power 4 all divided by the 4 factorial. Now see the change of the plot. The plot is slowly moving from a straight line to a curved line, a parabola. Then the parabola, the crest is slowly going up. Now I'm again going to increase the number of terms, minus x power 6 all divided by 6 factorial. Now see that it is not like a cos term, but I am going to again increase the number of terms, plus x power 8 all divided by 8 factorial. Now see this one. See, this cos function consists of only x term where the power is in multiple of 2, 4, 6, 8, and see the sign changes, alternately changing the sign from plus, minus, plus, minus, plus, minus. Now I am going to add two more terms. Let's say the more terms you add, the perfection of the sine function will slowly, gradually increase. So x power, I'm going to x power 10 all divided by 10 factorial, and again I'm going to add plus x power 12 all divided by 12 factorial. Now see this function. See this function. It's exactly look like a cos function, because when x equal to 0, cos 0, the function produce the value 1, and similarly here, see this one, it is coming down and crossing x-axis, and it is going up. So the more you add the terms you add, the function more close to the cos function. Now I'm going to add this one again, minus x power 14 all divided by 14 and factorial. So, okay, now it is, see that we produced almost two cycle of a cos function, and it is perfectly same. But when you look at the complete range of x, this is not exactly in the same way we expect. So that means we need to add more terms hereafter to produce the better cos wave function. Now let us try the simplified version of the Fourier series using the sum expansion function. So we will try this one, and we will add more number of n's by substituting value n from 0 to 20. So let's try that. Now this is the cos function. This is cos function is represented using the Taylor series expansion method, minus 1 power all power n, x power 2n divided by 2n factorial. So n is changing from 0 to 10. Let's see that how this function. Yeah, see this. So this is the cos function. Now I'm going to expand the number of terms from 0 to 10 to 0 to 20. Yes, the more you add the number of terms, the more the cos functions you can produce. But it's all finally it depends on the number of terms involved in that function. So now let's add the number of terms from 20 to 40. Now let's see this one. Yes, when you add more the terms, I change the number of terms from 0 to 40. See, the more the cos function is extended for a long period, and here so we can see that the Taylor series is perfect. The Taylor series is right, but the perfection of Taylor series also depends on the number of terms involved, and the more terms you add, if the numbers extend from 0 to 40, 0 to 30, 0 to 40 is more better compared to 0 to 30. So more term you add, the more perfect the cos function is. So more cos functions you can produce. So similarly, let's see. So here when x equal to 0, it is 1. So what is the difference between sine and cos Taylor series functions? Now let's see that. So I'm going to change this function. For a sine function, it is x power 2n plus 1 and all divided by, so it is so 2n plus 1 factorial. Now I'm going to change the number of terms from 0 to 10. It's okay. Now, yes, see the change. When x equal to 0, the sine function will produce 0. See, the variation of this function in the previous case was started from here. The function started from 1 when x equal to 0. Now the function started from 0 when x equal to 0. See, now it's this the function is perfectly look like a sinusoidal function, but we can see that only two cycles, 1 and 2. So from 0 to 10 will produce only 2 cycles. If I add the number of terms equal to 20, we can see that, yeah, the more cycles are produced, but see that the end. So now I'm going to increase from 0 to 20 to 0 to 40. The value of n is increased from 0 to 40 here. Now you can see that the more terms I'll produce, the more sine cycles I'll produce. That means Taylor series is perfectly right. So the only difficulties is if we have to add more number of turns to add more cycles. But we can use this one for any function, plotting any function in terms of summing infinitive number of terms to produce that function. Thank you. So please subscribe this channel for more future videos.